Everybody, I'm going to talk about the next system we're going to look at. That's the hydrogen atom and solving the Schrodinger equation. If you haven't already looked at the one for uh, the angular momentum and rotations, that's up on Moodle. So anyway, hydrogen atom Schrodinger equation can be solved exactly if we neglect relativistic effects, which we will, at least for now. Later we'll need them if we want to talk about spin. But as usual, what do we need? We need the Hamiltonian. It'll come in two terms as usual, kinetic and potential. The kinetic will look familiar, so we've got negative h bar over 2 mass of the electron in this case. So the nucleus is at the origin, so it doesn't move, and we only have the electron moving around. And then del squared, so second derivative, and the wave function is a function of radius, theta, and phi. And then plus a potential term. So here's a potential term, and we've got via R, which will be Coulomb's law, basically the attraction between the proton and the electron. So here is V of R. Coulomb's law, if you remember from physics, negative the charge of the electron times the charge of the proton. That's where the negative comes from because the electron's negatively charged. So, and they both have the same quantity, same charge as the charge in the electron. So it's just, this is just charge of the electron squared, and then some constants, 4 pi epsilon naught. That's just part of Coulomb's law. And then R, the distance from the nucleus to the electron. Then, of course, back up to the Schrodinger equation, we'll get the energy eigenvalues out and then the eigenfunction if we solve for it. And it can be solved. And conveniently, we can assume separation of variables. So there will be a product of three functions, which will be the wave function. So we have the radial function, the theta angular part, and the phi angular part. And as it turns out, the angular part is the same as a rigid rotor where we've got spherical harmonics. The radial part is a mess. And it's surprising that it's such a mess, but it is. So one thing that's cool is our other quantum number n appears here. So we've got three quantum numbers, the m sub l and the l in the spherical harmonics, but then also the n, the principal quantum number, comes in the radial part. L also resurfaces here. So those are both quantum numbers, minus 1, and that's a exclamation point for factorial over 2n, and then n plus 1 factorial, and that's a cube, and then the whole thing to the 1/2, and then, oh my gosh, so many constants. Some R dependence here, some R dependence here. And then what? Laguerre function? I don't know. It's another one of these famous mathematical functions that's been around for hundreds of years. And lo and behold, it pops up here. Constant A naught is called the Bohr radius, and that in and of itself is a collection of constants. Here you have the permittivity, Planck's constant squared, pi, mass of an electron, the charge of the electron squared. Anyway, Akamuts razor question mark. It's strange that it's so complicated, but it does work. And the eigenvalues pop out. The eigenvalues only depend on n, not L or m sub L. And I'll talk a little bit more about that. But you have this whole collection of constants, or it's also equal to this whole collection of constants, as it turns out. And then here's the final answer just in terms of all of those combined. And if this looks familiar, this is also the Rydberg constant, if I remember right, divided by n squared. So those are the energy eigenvalues. And the quantum numbers, n is called the principal quantum number, and it can be 1 and then any integer. Following that, it indicates the size of the electron cloud, also the energy. L is called the azimuthal quantum number, and that's the shape. It also is the angular momentum. So shape-wise, if L is 0, that's an S, and then P, D, F for 0, 1, 2, 3. M sub L is a magnetic quantum number, and that can go from negative L to positive L, and that says the orientation. So like for a p orbital, it can be horizontal, vertical, or in and out of the page. And m sub s is not needed to solve the Schrodinger equation. There's no m sub s in here. But we do know that when we include relativistic effects, m sub s will be needed, and that will tell us the spin. So we only need electron spin when we're accounting for relativistic effects, and that'll be spin up and spin down. So m sub s equals plus or minus a half, and you're familiar with that from Gen Chem. All right, so let's just take a look at the shape of the wave function. So you probably know some of this in general, but we'll look at it a little more quantitatively than in Gen Chem. So 1s orbital, L equals 0, m sub L equals 0. So this one depends only on R. So L and m sub L being 0, the spherical harmonic is just going to be a constant, no angular dependence. And then psi at R, we'll just have that radial part. Reminder, here's the Bohr radius, is all this stuff. And then that's 52.9177 picometers. So we know the Bohr radius to 6 significant digits. So that's the wave function. It just decays exponentially. Wave function squared also decays even faster. But for the probability, we also need to multiply by the volume element, and the volume element has r squared dr. So this is the volume element of a sphere. So then the probability function, when you multiply psi star psi dv, you have that r squared in there, so then the probability actually goes to 0 at the nucleus, which makes sense, right? That the electron can't be at the nucleus because the nucleus does get in the way. If we wanted to find out where it's most probable, we're just looking for this flat bit here. So you can take the first derivative, set it equal to 0, math, and you get r is equal to a naught at the maximum, and that's why it's called the Bohr radius. That's the most probable distance for the 1s cloud. Let's look at another example, 2p. So for p, of course, your L is equal to 1. That can only happen if n is equal to 2, because L can always, at a max, go up to n minus 1. And then m sub L could be negative 1, 0, or 1. We're choosing m sub L equals 0. Here's the psi. So you can see it's a function kind of 3 functions. You got r, you got e to the negative r, and you've got cosine theta. So here's the cosine theta function, what that looks like. Here's n times r is just a line, and then here's exponential decay on e to the negative r. So if you multiply these 3 curves times each other, you get a p orbital. So just the radial part is 0 down at the nucleus, and then goes through a peak and down, exponential decay. So this dominates at 0, this dominates at long r. And then you multiply that by the radial part. By the angular part. This part is not considered a node. I mean, it is 0, but I don't know. We don't call it a node. There will be a node, though, from the angular part. So we would say there's one angular node in the p orbital. So when your theta is at 90 degrees, you're going to have this whole plane is a node. So this whole xy plane is a node in the p orbital. No radial nodes. In fact, the number of radial nodes will be n minus L minus 1. So for a 3p, you do have a node here because n is 3, p, so L is 1, so 3 minus 1 would be 1. So you have the 1 radial node there. And so a 3p orbital, you have like this p orbital shape, and then it comes to 0, and then another p orbital shape. So you've got the radial node and the angular node. All right, probability calculations. We could, for example, try and find the probability that a 1s electron is within r equals the Bohr radius and r equals the Bohr radius plus a delta r, such that, I don't know, the delta V is 1 cubic picometer. So I'm looking at a spherical shell from A naught to A naught plus delta R. So we know delta V is equal to 1 picometer squared. This is the surface area of a sphere times a delta R. So this would be the volume of our spherical shell. Let's solve for that delta R, blah, blah, blah. It ends up being quite a small distance. But then probability, we've got 4 pi from the angular part, the integration of sine theta d theta d phi. And then from A naught to A naught plus delta R, you can integrate psi star psi, and then R squared dr is your volume element for the radial part. And when you integrate that, you get 2.9 times 10 to the minus 7. So that's like 3 billionths, 3 out of 10 million are your chances that you're at that Bohr radius within 1 cubic picometer. And if you want to check that yourself, you can pop that in there. Then normally at this point, I would ask a clicker question for which delta E is larger, and vibrational is larger than rotational, and electronic is larger than vibrational. And we know because rotational is microwave spectroscopy, which we don't do a lot of at this level. Vibrational is infrared, and then electronic will be UV vis. So that's how it connects: low energy to excite the rotations, more to excite the vibrations, and then even more to excite an electron from a low level to a high level. All right, just a couple more things. Degeneracy. So we know that the eigenvalues are just the Rydberg constant over n squared. It depends only on n. This is for the hydrogen atom, which has only one electron. If we have multiple electrons, then we know that we have further splitting with the L. But anyway, for n equals 1, we only have one s. And L equals 0, m sub L equals 0, so there's only 1. With n equals 2, we have 2s and 2p, and there are 3 2p's. So that degeneracy is 4. With n equals 3, we have 3s, 3p, 3 of those, 3d, 5 of those, so degeneracy is 9. 1, 4, 9. You can see the degeneracy, it goes as n squared. So 1 squared is 1, 2 squared is 4, 3 squared is 9. This won't be true when we add more electrons to the mix because of electron shielding. p orbitals will be higher than s, and d orbitals will be higher than p, which you know from drawing electron configurations in Gen Chem. All right, that's it for the hydrogen atom.